Good afternoon, everybody, and also let me thank Francesco and Cristina for the invitation. As anticipated also by Francesco, I will review the the properties of standard solar model, the status of standard solar model in connection with helioseismic data and solar neutrino measurement. Now, the fundamental theoretical tool in solar physics is the so-called standard solar model, which is a solution of stellar structure equations employing a well-defined chemical evolution paradigm according to which the sun was born as a chemical homogeneous and then it has evolved its chemical composition only due to nuclear reaction and elemental diffusion, and which implement a state-of-the-art calculation of the properties of the solar plasma, in particular the radiative opacity, the equation of state of stellar matter, and the cross-section of the nuclear reaction, which are relevant for energy production. The unknown quantities which are necessary to define this calculation scheme, which are the mixing length parameter. The mixing length parameter is a parameter which basically determine the efficiency of surface convection in the sun, and the chemical composition of the initial homogeneous ZAMS model are fixed through a calibration procedure. That is, they are chosen in such a way that the prediction of the solar model reproduce few observational properties of the present sun, which are well determined experimentally. In particular, the radius of the sun, its radiative luminosity, and the abundance of heavy elements at the surface of the present sun. Now, the important point is that after this calibration procedure, there are no free parameters. And so this means that the model is fully predictive. And this implies that we can falsify the prediction of the standard solar model by other independent observation, like, for example, the determination of the solar neutrino fluxes, the flux of neutrinos which are produced by hydrogen burning in the core of the sun, or by, for example, looking at the helioseismic properties of the sun. And indeed, through this kind of comparison with observational data, there was a constant improvement in the construction of the standard solar model, mainly triggered by the improvement in the constitutive physics during the last decades, which was due to the continuous comparison with solar neutrino and helioseismic data. Now, helioseismology is the study of non-radial solar oscillations. Several thousand different modes of oscillation have been detected. Their frequencies have been measured with very high accuracy, and through a linearization and inversion procedure, the information encoded in the helioseismic frequency can be used to extract selected properties of the sun. In particular, it can be used, this information can be used to extract the properties of the external convective region of the sun. The sun is radiative in the core and convective in the external region. Here, for example, we have the uniform helium abundance in the convective envelope of the sun. So the surface helium abundance of the present sun extracted from helioseismic data. Here, instead, we have the lower boundary of the convective envelope, so which defines the region of the sun where convection is active, as it is determined from helioseismic inferences. And also, we can extract the behavior of the isothermal sound speed, so the behavior of the sound speed across the solar structure as a function of the radius, with an accuracy which is at the level of 0.1% in a large region of the sun. Now, there was an impressive agreement till a few years ago between standard solar model prediction and helioseismic inferred quantities, and you can see here, these are the prediction of this specific standard solar model. I will come back in a minute to this, to the meaning of this acronym for the surface helium and the depth of the convective region, and also this is the this line here show the fractional difference between the helioseismic inferred sound speed and the sound speed predicted by the model, and you can see that the agreement is at the level of 0.1% almost everywhere in the solar structure. Now, the situation changed a few years ago as a result of a reanalysis of the surface composition of the sun. As I explained before, the solar surface composition is a fundamental input for a standard solar model calculation. The abundance of heavy element at the surface of the sun is determined with the spectroscopic techniques which require the construction of model of the essentially of the external layer of the atmosphere of the sun, which are rather complicated. At the beginning of this millennium, new models, three-dimensional, were introduced to describe the photosphere, and a lot of new effects which were not previously considered were introduced in the physics, to predict the line profile and then to extract the abundance of the different elements. And as a result of this, we got a composition which was quite different with respect to before. This is the old 98 composition, which correspond to this acronym here, the so-called IZ composition. And here elements are grouped in volatiles and refractory, so carbon, nitrogen, oxygen, and so on. And this is instead the so-called IZ composition, Asplund 09, which was produced by using this improvement in the description of the solar atmosphere. And you see that there is a systematic reduction of the abundance of all the elements, and this reduction can be as large as 30% for important elements in solar model construction, like oxygen, neon, etc., etc. The effect of the revised abundance is shown here. Now, this line corresponds to the fractional difference between the helioseismic inferred value of the sound speed and the prediction of the model with the old composition, while instead the red line corresponds to the more modern compilation. No? So the introduction of this new value spoiled the agreement with helioseismology, and this constitutes basically the so-called solar abundance problem. Why we do care about metals in solar model construction? Well, after all, they are a tiny fraction of the mass of the system. Nevertheless, they are important because they give a substantial contribution to the opacity of the solar plasma. Now, you have to consider that the sun is nearly homogeneous in metals. There is not a net production of metals in the sun. So the present sun has only, it's nearly homogeneous in metals with a slight enhancement of the metal abundance at the center due to elemental diffusion. So if you change the surface abundance of the sun, in reality, you change the abundance of metal everywhere in the sun. And metal, as I was saying, give a substantial contribution to the opacity, even if they are rare elements. Here, for example, we show the logarithmic derivatives of the opacity with respect to the abundance of a specific element or to the total abundance of metal in the sun as a function of the radius. So we see that metal accounts for about 40% of the total opacity at the center of the sun, but even for a larger amount at the level of 70–80% at the bottom of the convective region. And in particular, these elements here are very relevant in this region. This is the logarithmic derivative of the opacity with respect to the oxygen abundance or to the neon abundance. So when we change the chemical composition, we change the radiative opacity, the profile in the sun. The radiative opacity basically control the efficiency of energy transfer in the radiative region of the sun. So we get a different temperature stratification. So at the end, the sun can be hotter or colder depending on the chemical composition that we get, with observable consequences on the properties of the sun, and in particular on helioseismic quantities. Now, recently, 2 years ago, there was a reanalysis of abundances. One was performed by the Asplund, Amarsi, and Greves group, and the other one by an independent group Mag and Bergman and collaborator in 2022. These are modern determination of the abundances. So both these analyses are based on three-dimensional model and implement a state-of-the-art technique. Unfortunately, they give a non-consistent result among themselves. The value of the Amarsi group is closer to the old Lozed composition, while instead this new compilation is closer to the older IZ composition, even if not identical when you look at the individual element. So a solar composition dichotomy still persists, but is now, I mean, is based, I mean, it's really difficult to understand the origin of this discrepancy because both these determination are used are obtained in principle using a state-of-the-art description of the solar atmosphere. Now, this is the situation for what concerns helioseismic quantities. The blue line corresponds to the old IZ composition of Greve-Essence Wall 98. The red one is the Asplund 21 compilation, Amarsi Asplund 21, and Mag Bergman give a final result which is very close to the old one. And here we also have the prediction for this different model with some variance which can be considered for the depth of the convective region and the surface helium abundance. So you clearly see that IZ surface composition provide a better description of helioseismic data. Now, can we conclude, due to this result, that the low Z composition is simply wrong? Unfortunately, it is not simple to arrive at this conclusion because the interpretation of the helioseismic result is complicated by the fact that effects related to composition are degenerated with effects related to a recalculation of the opacity. As a matter of fact, the sun responds to the total modification of the opacity profile, which can be partly due to the fact that the composition is different for what we expected. We call this the composition opacity change. This is the effect induced by the change of composition, or it can have an intrinsic contribution simply because the calculation of the opacity for a given composition are not accurate enough. No? So when we try to address this solar abundance problem, we should ask ourselves whether the opacity of the solar plasma is sufficiently well calculated. To note that not only the overall magnitude of the opacity is important, but also the shape of a possible opacity variation can be very relevant in this problem. This kind of point was raised in this paper, where in particular, by using different technique, we calculated the opacity kernels which allow to determine the effect on a given observational quantity of an arbitrary variation of the opacity profile. So at a linear level, you expect that if you modify the model by introducing this kind of global opacity variation, the model responds by producing a certain a new prediction for the different quantity, and so a fractional variation of the generic observable, I mean, which could be the surface helium, the convective radius, the sun speed, or the neutrino fluxes. Now, if you look at this kernel, what you discover is that they have, in some cases, a complicated structure. This, for example, describes the response of the sound speed at this radius with respect to a modification of the opacity, etc., etc. In particular, what you see is that the kernels are not positive definite. You have here, for example, this one is negative, then is positive, and then is again negative. So this basically means that you can have a compensating effect if you consider broad variation of the opacity, and this is exactly what happened. In particular, the sound speed is insensitive to a global rescaling of the opacity. So the old recipe of estimating the uncertainty in solar model calculation by simply multiplying the opacity by a certain fraction up and down give greatly underestimate the total error due to opacity. The same situation is for the convective radius. Fortunately, other quantities like the surface helium abundance and the neutrino fluxes instead depend on positive definite kernels and depends on the global opacity scale. So at the end, one, when one considers the global picture, one has that all the solution of the solar abundance problem, either due to a composition variation or to opacity recalculation, should have this kind of features, no? With respect to a model with the low Z abundances, one would need an increase of the opacity at few percent in the center of the sun. The scale is fixed by the solar neutrino flux measurement or the surface helium abundance, but then this kind of variation of the opacity should be much larger, so the opacity variation should be not only increased but also tilted. It should be much larger at the bottom of the convective region at the level of 20% in order to explain the sound speed and the convective radius data. In our latest standard solar model calculation, we take this into account by parameterizing the uncertainties in the opacity in this way, as a scale plus a tilt in log t. These are two random variables which were chosen in such a way to have this kind of behavior for the opacity uncertainties, to take into account that at the center the opacity is better determined than at the surface. As I explained, this was done in order to avoid underestimating the opacity error contribution to sound speed and convective radius. And so it was an improvement with respect to before, but it has to be, it still remains a very simplified description of the true situation. Here, for example, superimposed to this band, I show the fractional difference between different opacity tables along the solar composition, along the solar profile, and you see that there is a complicated structure, so the reality may be much different with respect to this, okay? So we have this problem with opacity. What can we do? Well, neutrino can help us. Okay, we all know that neutrinos are produced in the sun by nuclear reaction transforming hydrogen into helium-4. There is for each helium-4 nucleus which is produced, 2 electron neutrinos are emitted and a given energy is liberated in the plasma. As Aldo explained, we have two main mechanisms, the PP chain, which is responsible for about 99% of the total neutrino and energy production, and the CNO cycle, which uses carbon, nitrogen, and oxygen nuclei as catalyst for hydrogen fusion. The CNO cycle is responsible for about 1%, but it's a fundamental process in astrophysics, as we all know, because it's the dominant energy producing mechanism in star more massive than the sun or in more advanced evolutionary stages. Here we have the solar neutrino spectrum. These are the different components. This is the theoretical error in the prediction. The black line are the component of the solar neutrino flux produced in the PP chain, while the blue and the red one are instead produced in the CNO cycle. With respect to the standard plot, I added here two red lines, which are usually neglected, which correspond to the neutrino produced by electron capture reaction within the CNO cycle, which can be interesting even if they are beyond the reach of present detectors. Okay, Aldo explained very well that a lot of experiments measured these fluxes, and what we have now is quite a good knowledge, which can be extracted by fitting the experimental data on the different fluxes. These are the results which have been presented by a recent analysis, which is contained in this paper, where they fit the solar neutrino experiment by taking as free parameter the flux of the different components, obtaining this result. The first table is obtained implementing the solar luminosity constraint, while instead the second one is obtained not implementing the solar luminosity constraint. And I will come back to this point because it's connected to the importance of having measured for the first time with Borexino in a direct way the PP neutrino fluxes, which is the major component of the solar neutrino flux. Why this is so important? Well, because it allows us to test the stability of the sun or energy conservation in the sun. No? If we assume that the sun is stable, indeed, we should expect that the amount of energy which is radiated at the surface of the sun with through the photon emission or neutrino emission or by additional possible exotic energy losses should exactly match the amount of energy which is produced in the interior of the sun by nuclear reaction. This additional term is the gravothermal energy production, which is a tiny fraction of the total because the evolution of the sun is very slow. No? Now, these terms can be either measured or calculated, as it is described here. In particular, the neutrino fluxes traces the efficiency of nuclear reaction, and now that we are able to measure all the different components, and in particular the measured component of the solar neutrino flux, which is the PP neutrino component, we are able to test the validity of this relationship. Which here is rewritten in this term. No? So we can use the neutrino flux determination to calculate the right-hand side and to compare with the left-hand side, testing the solar stability, the global energy balance of the sun, and the presence of additionally energy losses or sources which may be not included in the standard solar model calculation. At the moment, thanks to the recent measurement of Borexino, the neutrino infrared luminosity, which basically correspond to this right-hand side, is determined with an accuracy which is at the level of 7%. Okay, this independently on any assumption. Okay, in addition to PP neutrinos, we also have an high accuracy determination of boron and boron 8 and beryllium 7 neutrino fluxes, this component here and here. This can be used to test standard solar model calculation and to verify that the properties of the sun are correctly predicted by solar model calculation. Here I am comparing the experimental result, experimental infrared value for the fluxes of these two components with the prediction which are obtained by IZ and LOZ standard solar model. And you see that the experimental determination unfortunately lies in the middle, and this is one of the reasons why it is not able to discriminating in between these two predictions. But it's not the only reason. The point is that despite the high accuracy of the experimental determination, the possibility to discriminate between these two predictions by looking at these fluxes is prevented by theoretical uncertainties, which dominate the error budget. These fluxes basically depends on the central temperature of the sun. The difference between the central temperature of IZ and LZ standard solar model is at the level of 1% or less, and the uncertainties on the environmental parameter of which are necessary, in particular on the opacity, okay, which are used to construct standard solar model, prevent to have a prediction of this quantity with sufficient accuracy. This is seen here. No? Theoretical uncertainties, as I was saying, dominate the error budget. These are due to surface composition and environmental parameter, in particular the opacity. And so if you include this, you see this kind of effect. And then we have a contribution from nuclear cross-section. So you see that at the end, the prediction the theoretical uncertainties prevent the possibility to discriminate between these two models. And at the end, the problem is always the same, is the fact that these fluxes depends on the central temperature of the sun, and the central temperature of the sun depends on several parameters, among which opacity, and opacity can be affected by composition or by calculation of the opacity, so we cannot discriminate by using these fluxes the two effects, okay? The situation has changed recently with the determination of CNO neutrinos, which was performed by Borexino. And that's why they are so important in this respect. The point is that CNO neutrino fluxes, besides depending on the central temperature of the sun, okay, and on the cross-section of the bottleneck reaction of the CNO cycle, they also have an additional dependence, which is specific for them, on the chemical composition. This is due to the fact that CNO neutrinos, that the CNO cycle use carbon and nitrogen, which are present in the core of the sun, of catalyst to produce hydrogen fusion. So the overall efficiency of the CNO cycle depends on the amount of carbon, the number, basically on the number density of carbon plus nitrogen elements in the core of the sun. Okay. And then here I'm showing the chemical composition of the present sun as a function of the radius. We have that at the center of the sun, almost the entire amount of carbon-12 originally present has been transformed into nitrogen-14 in order to fuel this reaction and to make the cycle more efficient. But the total amount of this quantity is not changed by the efficiency of this cycle, so it remains constant. So nuclear reaction do not alter this quantity. So this quantity here is really a record of basically the composition, the initial chemical composition of the sun, only modified due to elemental diffusion from the, okay. So this extra dependence allows us to extract the solar composition independently on assumption on the other parameter, and so to break the composition opacity degeneracy. So the combined measurement of PP chain and CNO cycle neutrinos can be used to test directly solar composition. The basic idea is that one can use the dependence on the central parameter of the boron neutrino flux and its determination to infer the central temperature of the sun, and then the extra dependence of the CNO neutrinos on the composition is used to infer the chemical composition of the solar core. In practical terms, one can form a weighted ratio of PP and CNO neutrino fluxes. Here we are considering boron 8 and oxygen 15 neutrinos, which is essentially independent on the central temperature of the sun, which basically means essentially dependent on the environmental parameters, including opacity, and directly proportional to the carbon-nitrogen abundance of the solar core. Okay. What we cannot cancel is the dependence on the cross-section, which determine the efficiency of the CNO cycle and of the PP chain, because these are different within the two mechanisms for energy production. Okay, so now that Borexino has measured this quantity, this kind of approach has become possible, and it has been applied by Borexino collaboration. Here we have the rate of the CNO signal measured by Borexino rescaled to the prediction of the GS98 solar model. By using this number together with the value of the boron neutrino flux, which is obtained by global analysis of solar neutrino problem, one determine this value for the carbon plus nitrogen abundance of the core of the sun rescaled to what was implied by this kind of compilation. And the Borexino result is reported here. So we see, this is the result, so 1.35, so it's larger than 1. So Borexino data seems to indicate that the amount of carbon and nitrogen in the core of the sun is even larger than what expected according to the IZ compilation. This is the error budget, which is dominated by the experimental error, and it has a 10% contribution from all the other sources, which is basically dominated by the nuclear reaction uncertainties, with the largest contribution provided by this reaction here. And here we compare the result which are obtained by applying this method with what is obtained in the different compilation. So we see that CNO data give an indication in favor of the IZ composition, even if the uncertainties in this determination, I think, is still too large to exclude any of the possibility. This is the same plot, and here there is a discussion of all the contribution to the error budget. Yes. Yes. Also, these are 1 sigma. This is 1 sigma error contribution, etc., etc. So, in conclusion, Borexino has opened the way to CNO neutrino detection, and this is very important. Unfortunately, Borexino is no more running. We may hope that in the future there will be improvement on the experimental side. There are experiments that will have a solar neutrino program. Unfortunately, the detection of CNO neutrinos is very difficult because it requires, as Aldo explained, a lot of characteristic, very high purity, deep detectors, etc., etc. In this context, let me say that there are some minor components of the solar neutrino flux which are still undetected, and some of them may be addressed by future experiments, like in particular the HAP neutrino and the electron capture CNO neutrino, the neutrino produced by electron capture reaction in the CNO cycle, which in my opinion are very interesting because they encode essentially the same information as conventional CNO neutrinos on the chemical composition of the sun. But moreover, they are monochromatic. And so in principle, if they are detected, they could help to extract the survival probability of solar neutrinos at a well-defined energy, which is approximately 2 MeV, so in the middle of the transition region. So in principle, it is a very difficult task to observe this object, but it could be rewarding in terms of physical implication. And in order to observe this neutrino, it will be required to have a gigantic ultra-pure liquid scintillator detector, which should be as clean and as deep as Borexino and as large as Juno. So in this paper, we show that in principle, in a detector like this, it would be possible to observe this signal. Okay, so here I have my conclusion. Solar neutrino physics entered the precision era. Borexino has opened the way to CNO neutrino detection. And this is important because it could give clues for the solution of some long-standing problem like the solar abundance problem. To the full potential of future measurement, it would be necessary also to have improvements in standard solar model constitutive physics, in particular nuclear cross-section and radiative opacity. And in this context, I also want to advertise that it was recently released, this new paper, this new compilation of nuclear reaction cross-section, the Solar Fusion 3 paper, which is available on the net with this data. Thank you very much.
Thank you very much for this very interesting talk. Time for questions. Yes.
Thank you, Francesco. So just a curiosity. So the Borexino measurement of the CNO show a larger amount to respect the expected one, no? To the standard model. And so this CNO component is mainly in the center of the sun, right? So this is an increase, this is also an increase of opacity in the center as you need?
No.
There is no any correlation?
It cannot be produced, this kind of effect cannot be produced by an increase of the opacity. This is the point, because if you only touch the opacity, you increase not only CNO neutrino, but you also increase boronate neutrinos. Okay, so the fact that the ratio between CNO and boronate neutrino deviates from expectation cannot be cured, cannot be modified by any possible modification of the opacity profile. It requires a different composition, a different chemical evolution paradigm, different reaction cross-section and so on, but it cannot be addressed by a modification of the opacity. In more quantitative term can be seen here. These are I've not commented this plot, these are the opacity kernel of the different neutrino fluxes, and you see that the shape of the opacity kernels of CNO and the boronate neutrinos is identical. So if you make this ratio, all the possible modification in the ratio of these two fluxes connected with opacity have no effect. Okay? So that's why this measure is potentially so important in this problem. Okay? And that's why I was saying, in principle, in connection with sorry, Georg, to the question that you were raising before, that in principle, the astrophysics community, a large part of the astrophysics community would prefer to decide that low Z abundances are right with respect to high Z abundances. They trust more, okay? But they still have not understood that they cannot, they cannot change, no, by an opacity modification the relative ratio of these two neutrino fluxes, and so that the neutrino measurement is potentially a problem independent on any possible variation of the opacity profile of the low Z abundances. Okay.
Francesco, just a minor comment, but you told correctly that these elements are a small fraction of the mass of the sun, no? But
Yes.
I would say that even psychologically, it should be remarked that most of the metals that we have in solar system are inside the sun, not in the planets, no? So in a sense, we are for the first time probing somehow what is the composition of the solar system to some extent.
Exactly. And in some sense, the most intriguing solution of the solar abundance problem could be related to this point here. Maybe this problem could tell something about the chemical evolution paradigm that we are assuming, which is also related to how to the solar system formed. Okay. This is if we discover that the kind of modification which is necessary, is of this kind, this is an important point, because it would tell you that this kind of scheme, which is basically is applied to all the stars that we observe in the sky, no, it's not correct. Maybe it's oversimplified. It should be complicated, etc., etc. And also, they could tell us something about the formation of the solar system and so on. At the moment, we are not still there because uncertainties are large and etc., etc. There is, to be completely honest, there is a caveat in the argument about CNO, neutrinos, etc., etc., which is the following. In reality, CNO is true. CNO neutrinos are sensitive to the composition of the solar core, but they are mainly sensitive to carbon and nitrogen. And the reason is that only the CN branch of the CNO cycle is active inside the sun. While instead the element which is most important for the solution of the solar abundance problem is the oxygen. It's very plausible that the evolution, or the chemical evolution of this element is connected, and so if you rescale this, you expect to rescale also this. But helioseismology is probing this element. Solar neutrinos are instead connected with the abundance of these two elements here. So if you break this connection, then you are in trouble. If for some reason the relative abundance of this element is not correct, maybe you can find a solution of
Yeah, Sergey.
What are the prospects of improving the precision on the cross sections?
The cross section. These have been okay. We just had this new computation. Honestly, I'm always. I participated also to this work, but the technical work related to the interpretation of the data for each specific reaction has been done by others. Honestly, looking from outside, I'm always really impressed on how good they are. Because during the last 30 years, we went from 20% uncertainties of the relevant nuclear reaction to 10%. Now we are at the level of few percent, 4 or 5% uncertainties. The dominant, in this game, the dominant contribution is given by this reaction. This is determined with 7% accuracy. The other are at this level, and so on. In principle, to do better, it's becoming more and more difficult, because we are sitting on the shoulder of giants, which have already done an impressive job. But in principle, this kind of approach, at a certain, if one would be able to improve the experimental determination, then it's limited by this kind of
the Luna project, and then there is something in Germany, I think, in Dresden.
Yes, they are working. They are going to remeasure some of these processes. In particular, with respect to the old days, this one, has changed. It was originally believed to be much larger, this cross section. If you look at all the paper, maybe you get that the CNO neutrino fluxes, which was predicted by standard solar model, was twice as large as now, and it was related to the fact that this was not measured and was believed to be much larger. But now they are constantly improving this measurement.
Maria. well, a bit more clarification on composition and opacity, because you say at some point that modification in the composition and modification of opacity are somehow degenerate because sometimes they produce the same results. But then my question is, the opacity does not depend on the composition. I mean, if I have an heavy element, it's not that automatically I have even more opacity.
Yes, but that's why you have this kind of effect. In principle, to solve the to calculate a standard solar model, you need an opacity table, which means you need to know the opacity as a function of density, temperatures, and chemical composition for all the possible range of parameters which are relevant for solar model construction. Okay. Now, just consider that the metal abundance is more or less constant, and so if you fix the surface composition, you are fixing the chemical composition of the sun, I mean, with 10% accuracy due to elemental diffusion. And if you change so the surface composition, is I mean, you are moving to another value, and it's like if you're moving in a different path in this parameter range. But the point is that opacity calculation are affected by large are very, very difficult opacity calculation. I mean, again, it's something which is surprising that they can calculate, because in principle, in order to calculate opacity, you have to, opacity is connected with the absorption length, the free path of the photon in the solar plasma. So you have to calculate all the possible processes at all the possible energy of interaction of a photon with all possible elements which are partially ionized, etc., etc., etc. So it's really a complicated task, no?
Yes, but it's a derived quantity in any case. The fundamental quantity is still the composition, the temperature, and something else. The opacity is just a derived thing. You treat it somehow like, I mean, you
have to take into account that you have this kind of, I mean, if you change the composition, you change also the temperature and the density profile, and so everything is correlated, but this is done. Okay. When we calculate this opacity kernel, we take everything into account and so on, that if you perform a modification, everything should be self-consistently readjusted in order to, so you move to a different path, etc., etc. Yeah. At the end, I mean, the source term goes here. In this paper, this one, we linearized the stellar structure equation. We created what we call it the linear solar model, no? And in this scheme, you are able to see which are the source terms for any possible modification. And if you do things properly, you get that the source term, which is responsible for a possible modification, in this sector, which is the one which is related with thermal stratification, is given by the sum of these two elements, and then by using this linearized approach, you are able to extract this kernel for any generic.
Okay, and just another question. When you show this work by Concha 2024, you show all these fluxes, no? Yes. And all calculated in two different ways, with assumption and without assumption.
Yes, it was a little bit fast.
My question is, are they compatible? So the fluxes that you have above and the fluxes below are always compatible, or there are cases where they are not? Because in one case, I see the error are much larger than the other. Mm.
So, okay, here, all the fluxes basically are free, but here they are assuming the solar luminosity constraint, which basically means that they are assuming that this relationship is valid. Okay? Mm-hmm. So this automatically implies that since this quantity is determined with very high accuracy, the measured component of the solar neutrino flux, which are PP neutrinos, is basically constrained by the measurement of the solar luminosity and not directly by the Borexino measurement. And indeed, what you see is that if you use the solar luminosity constraint, the PP neutrino flux is determined at the level of 0.4 per mil. 0.4 per mil is 0.4%, which is the level of accuracy of the determination of the luminosity of the sun. Instead, if you do not implement the solar luminosity constraint, you have that the error is at the level of 7%, which corresponds to the Borexino measurement. So the major difference between these two lines is related to this. Then if you go instead to boron and beryllium neutrinos, which are subdominant and very well determined by experimental data, you should see that the accuracy 2%, 2%, 2%, 2% is essentially the same, whether you imply or not the solar luminosity constraint. So the major difference is related to these two fluxes here, and also to the PP neutrino fluxes, because normally they are linked to the PP neutrino, since the producing mechanisms are connected. You know? In one case you have PP into deuterium, in the other you have a P plus electron plus proton into deuterium, etc. So there is a strict connection from the point of view of nuclear physics. So they are linked together in the analysis. Here the results are normalized with respect to the prediction of the standard solar model implementing the new IZ composition, so Magge-Bergman. So you see that the CNO neutrino fluxes are even larger than the Magge-Bergman production, even larger, as you expect, due to the Borexian result, than the prediction with the IZ composition.
But what is the difference between Asplund and Magge-Bergman composition? In brief.
In brief, from an external point of view, honestly, they fight a lot. If you speak with them, they say that this is completely wrong. If you speak with them, they say that this is completely wrong. Honestly, I really think that at the present time we are at the limit of which you can, of what you can say, in the sense that then the choice of the lines that you are considering, in very subtle effect, make the difference. So from the point of view of a person which is using these things and which is not measuring, it's rather, I mean, uncomfortable. I think that they claim that Magge-Bergman are not completely autoconsistently three-dimensional in all the treatment that they do. They discuss that they are using some lines which are should not be used because they can be some spurious effect and so on. So it's really very complicated to understand who is right. I mean, for me, it's, I mean, I would like to have other indication in favor of one or the other.
Okay, just I have the microphone in my hand. I remember that. Sorry. I remember that I had a discussion with Frank Alaprice about this S114 factor a few years ago, and he mentioned to me some experiment on surface in the USA, which reported a value slightly larger than what was measured by Luna 400. Now this will be remeasured, this cross-section. But he mentioned to me this a little bit higher value, and in fact he was considering this to be remeasured, very important to maybe support a bit larger CNO flux. I don't know if you are aware of this.
I'm not able to track all the change, but in the latest standard solar model calculation that we presented in 2016, we were using a slightly updated result with respect to the Solar Fusion 2 paper, because there were in the meanwhile there were other measurements, other analysis, and so on. And now this value has been refined a little bit more in the Solar Fusion 3 paper, slightly decreased, but not really, I mean, in a significant way, if I remember correctly.
Francesco, a few years ago with Saivescovi, we had the calculation on electron capture for beryllium production. I don't know whether this was considered in the new assessment or was not. No,
but if I remember correctly, the effect on the sun was very small. No, if I remember correctly, in the beryllium, I don't know, maybe the Barcelona 16 paper was before, or I don't remember. In the new one, the one which have been, actually the new standard solar model we still should present, but some results have already been used by Aldo in the calculation of this table which was presented before, and I don't think that he touched these things.
Okay. If other questions? If not, so let us thank Francesco.